downstream of the cerebellum, which is really the output station for the cerebellum. This is called what some people call it the DN, the deep nuclei, or the DCN, which is the deep cerebellum nuclei. And again, these structures are affected, but also what you see is most of these patients actually don't die of the neuronal deficits. Most of them actually develop this persistent cardiomyopathy, and so they just essentially die of heart failure. Okay, and again, that's because here you have a structure that is constantly active, or at least I hope it's active all the time, and there's a huge sort of metabolic load in terms of the cardiomyocytes there. And this is another place where you sort of see high levels of potassium. So, in actual fact, if you go in and you look at tissue, and this is what I said to you before, some of these structures, such as motor neurons, sensory neurons, the cerebellum, the heart, are the places where you see the highest levels of potassium in the fetus and also in the adult. So those are the tissues that seem most susceptible to the loss of it. Okay, so what we have up here is some dorsal root ganglia. So the dorsal root ganglia contain the sensory neurons from the peripheral nervous system that really innervate, both the musculature they innervate the musculature in our body, and also all of the sort of the cutaneous receptors that are important for sensing pain, touch, temperature, and those types of things. But the ones that actually, and you can really sort of see the most prevalent loss here, so the ones that innervate the muscle, and these are the ones that are probably most important for motor coordination, are the large diameter sensory neurons. Okay? And so these are the ones that you can see over here. You can see they've got these sort of thick myelin sheets around them. These are the big guys, over here. So what you can see is that this is taken from Friedreich's ataxia tissue, and you can see here. You can see a lot of these large myelinated fibers and neurons that are found within the dorsal root ganglia, and you can see that these are very much reduced in number in these. And that's really indicative of that these large myelinated sensory neurons, which we call the proprioceptors, these are the ones that are dying. And proprioception is incredibly important. So proprioceptors is the way that it's the way that we sense self and position. So you close your eyes, and you know where your hand, where your arm is at any point in time. It's actually proprioception is from the Greek term self. It's a sense of self. Okay, and without it, you're completely ataxic. The only way that you can walk is if you actually look. And you have to look at your feet and you actually have to look and use them to move. And there are a number of patients out there, that have been identified now that actually have sort of deficits in proprioception. And it's, as I said, these patients have great difficulty in executing any sort of movements. Now, part of the reason I'm sort of pointing this out is that, let me just go through this, some others. This is actually from a mouse. This is actually from the paper you're going to look at. And what you can see in this mouse model is that you see degeneration in the cerebellum. You can see it in the granule cell layer, so this sort of these dark areas here. In the granule cell layer, you see them in the Purkinje cells here, which is the main output cell of the cerebellum. These Purkinje cells over here express a protein, calbindin. This is a calcium binding protein, and these calcium binding proteins are typically expressed in cells that show very high neuronal activity. Actually, I should have pointed out that the sensory neurons, the classic marker for those proprioceptive sensory neurons, is another calcium binding protein which is called parvalbumin. Okay, and so that's a sort of a common feature that we see in neurons that are active, is that they actually have to have very strong calcium buffering. But essentially what you can see is that in these patients, this is a wild type over here, and you can see in these patients, you can see a marked reduction in the number of Purkinje cells. The actual Purkinje cells are abnormal, and there's sort of reduction in some other structures, reduction in the thing over here which is called Clark's-Collin, and other cells that are found within the spinal cord. You can see motor neurons up here. These are motor neurons that are in the process of dying. You can see they're sort of they're darkly labelled here. It's very hard to see over here, but you can see some big cells over here, and those are actually healthy motor neurons in a wild type mouse. Okay. Now another structure, and this is actually taken from a human patient, and what you can see here is this is the normal tissue over here. This is the cerebellum. This is we were looking at, this is where the granular cells are, the Purkinje cells are. And you can see there are a lot of folds in here. What you can start to see in these patients, the first thing you're going to see is you're going to see this dentate, which is the output cell from the cerebellum. So the Purkinje cells project to these. You can see that this is much smaller than in a normal patient, and you can also see these big gaps, and there's sort of less folding, and there's actually sort of abnormalities and tissue loss from the cerebral cortex itself. So you can see that there's degeneration that's ongoing in there. So here we are. So this is actually, just pointing out sort of what our sensory system is. We have these, in our dorsal root ganglia, we have these sensory neurons that project into the spinal cord. And in actual fact, one of the major pathways, you actually have a number of pathways, but a lot of the proprioceptors that come into the spinal cord. So, so here's our muscle sitting over here. We have our sensory neuron. Here's our DRG here. Okay, and we have our spinal cord that's down here. This goes into the spinal cord. This one goes into the spinal cord, and there's a direct pathway, actually, that goes up, and that goes up to the cerebellum. And then there's an indirect pathway that goes to another neuron, and this is the neuron that's in the Clark's-Collin, and that also projects up to the cerebellum as well. Now, what is a sort of a characteristic feature of all these neurons is that when you go and try and make a recording from them, what happens is that these neurons are just continually active. They're just firing the whole time. Okay? And so they, it's just like, well, I say that because, the way that physiologists often listen to a neuron, if you're making a recording from the neuron, you actually have an audio output. And so, you can go in, and it's really cool, so you have your tissue there, you go in, and you put your electrode in there, and then when your electrode gets in, and the cell starts, and you know that you're inside the cell, or you've made a patch on the cell, and the cell is actually actively firing, you can just suddenly, you just get this, rapid firing if the cell is kind of tonically active. And these cells seem to be sort of tonically active. Okay, so essentially you have this pathway coming to mossy fibres, coming up into the cerebellum, into these granule cells up here. I'm not going to go into too much detail. Into the Purkinje cells here, into the deep cerebellum nuclei here. What we know is that this pathway is very important for controlling movement, and as I pointed out to you, is that these cell types are constantly active, and so they're particularly susceptible to neuronal cell death. And this just gives you a sort of an example. This is what your Purkinje cell is doing when you're at rest. This is an inhibitory neuron, and as I said, each of these little sort of vertical bars is that neuron firing a single spike. So you can see that at rest, your Purkinje cells are basically just going, all the time. And when you initiate a movement, essentially what happens is you turn off the Purkinje cells, and that allows you to activate, in this instance, neurons in the deep cerebellum nucleus. But again, you can see these cells are also pretty active, even both at rest, but also during movement. Okay. So, as I pointed out to you, tissues with high oxidative requirements typically are affected by mitochondrial dysfunction. Another example, and I think Sam Fatt will talk a little bit about this, is Lou Gehrig's disease, ALS, which affects motor neurons. And this is another class of neurons that are active. I talked about Parkinson's, Leigh syndrome, which is a basal ganglia dystonia. And again, this is a mitochondrial, this actually gene is encoded by the mitochondrial DNA to ATP synthase, and again, leads to mitochondrial function, mitochondrial dysfunction. I think we're going to be ahead of schedule here. Okay, for the last part of today's lecture, what I want to do is I want to take you back and really sort of just talk very briefly about Parkinson's and about mitochondria and mitochondrial dysfunction. So, if you remember when we were talking about Huntington's on Tuesday, one of the key genes that seems to be important in the pathogenesis of Huntington's is this gene called PGC1 alpha. Okay, and PGC1 alpha is a gene that is very important for synthesis and the production of a lot of these nuclear proteins that are important for the production of mitochondria. PGC alpha, if you look at it, it's expressed at very high levels in cardiac tissue. It's also the gene that's expressed at very high levels in slow muscle. And slow muscle is that muscle that is metabolically active all the time. Okay? And so this gene is actually known to be essential. If you actually get rid of PGC1 alpha, you can turn slow muscle into fast twitch muscle. Okay, so this sort of just outlines here what is a sort of a normal mitochondrial or life cycle within a cell. And mitochondria are constantly being turned over within the cell. And the way this is done by a sort of somewhat arcane process, where you actually have this combination of fission and fusion. And that is that you can compartmentalize the mitochondria. And so those components of the mitochondria which are damaged, you can actually sort of compartmentalize them within the mitochondria. You you then undergo a sort of a fission. So here you can see something over here. This is the mitochondria. One part of the, the mitochondria is sort of accumulating damage. Essentially what happens is that the damaged elements of the mitochondria kind of get sort of concentrated. And I don't know how this occurs. In one area of the mitochondria, you undergo sort of a fission where the sort of crappy part of the mitochondria gets targeted to the autophagosome. So basically, it gets removed, and then this other component is then new elements that are produced and transported to the mitochondria and get inserted into the mitochondria to produce, supposedly a new reconditioned mitochondria. And so this is this kind of constant life cycle that's ongoing in your body. Okay, so this is actually taken from a recent review in Neuron by Pickrell and Yule. And they've done a lot of work on one particular pathway that seems to be really important, or it seems to be very important for mitophagy, for the regulation of mitophagy. And there are two genes within this pathway that were originally identified in patients that develop early onset Parkinson's. And this is actually first identified in a cohort of Japanese patients, and these patients actually had mutations both in a gene which is called Parkin, and then another gene here which is called Pink1. But it's actually these two molecules actually play a really sort of interesting and neat role in regulating. It's basically like a quality control program that monitors and regulates mitochondria and the production, the generation or the sequestering of bad mitochondria and the generation of new mitochondria. And I'm going to just sort of tell you a little bit about how this occurs. So these two proteins actually kind of work together. So essentially what you have is you have our mitochondria here, you have our inner membrane here, and we have our outer membrane, and essentially what one has is that there is a sort of a receptor or a pore on the mitochondria. There's these two mitochondrial proteins. One's called Tom, and one is called Tim. Okay, and what happens is that there's a kinase. Pink is a kinase, and it's a ubiquitin ligase kinase. Okay, and so what happens is that the pink protein is normally inserted into the membrane, and when it's inserted into the membrane, this is pink over here. This is where my drawing is. Okay, so let's have our pink protein with its kinase function that's sort of sitting in there. So what happens is that there's another protease called PAL, and PAL is an inner membrane protease, so it's found here in the inner membrane. And what PAL is able to do is it's actually able to sort of cleave a pink here and pink then gets sort of released and sort of degraded. Okay, so now a typical feature when mitochondria are sort of starting to degenerate is that the membrane potential between the inner and the outer membrane starts to collapse. Okay, and when that membrane potential starts to collapse, what happens is that the pink is not properly inserted into the membrane and cannot be cleaved. So it actually only gets partially inserted into the membrane. It tends to associate more with Tom than with Tim. And as a result of that, there's no cleavage by Carl. And so now what you start to see is the whole outside of the mitochondria begins to be decorated with the pink kinase. And you can kind of let's just go back up here. So what's happened here is the mitochondria have been damaged. These might be due to mutations in mitochondrial DNA, oxidative stress. There's this reduction in the membrane on here. And so it seems that now what's going to happen is you get things begin to accumulate on the outer membrane of the mitochondria, and this actually drives two processes. It drives just the classic ubiquitination that you see, but Parkin is also a ubiquitin ligase over here. Okay? It's an E3 ligase. And E3 ligases, as you know, are very important for activating this ubiquitin pathway, which is a protein degradation pathway in cells. So what happens is that Parkin then is recruited to the surface. It's actually phosphorylated by the pink kinase. It's accumulated on the surface of the mitochondria. Okay, so it's activated, and what this does is that this targets these cells to be degraded here in these autophagosomes. Okay, so you see an increase in mitochondrial degradation. So under normal circumstances, this is a sort of a very nicely balanced process. And as I said, you actually have this mitophagy cycle where you have this very nice sort of quality control system that's sort of finely balanced in place, where mitochondria, when they get damaged, those portions of the mitochondria, undergo fission. They can sort of get left off, they get targeted, and then you get the production of new mitochondria to replace the damaged mitochondria. So what you can see over here is in a healthy cell, you sort of have this nice balance between the removal of these damaged mitochondria and the production of good mitochondria. In the case of Parkinson's disease, you can actually have two processes. So the first is that you just get increased mitochondrial damage, and that begins to overwhelm this. And then, as the Parkinson's progresses, you have this mitochondrial damage, and you get this increased, removal of these, or an inability to remove these damaged mitochondria. And so now what you have is you start to see an accumulation of non-functional mitochondria in those cells, and that eventually leads to cell death. So I hope actually, in terms of some of the take-home messages from this lecture, what we sort of take home from it is something about the mechanism, the fact that mitochondrial function seems to be a very important driver of neurodegeneration, so the loss of mitochondrial function. The fact that the cell types typically effective in various syndromes, are often cell types that are metabolically active or have high firing rates, so they tend to be more susceptible than cells that are only episodically active, and that that some of the defects in terms of transcriptional regulation and gene expression that we see in those converge again on genes that are important for mitochondrial function. And I've mentioned sort of two of those genes. One is PGC1 alpha, and the second example here is frataxin in the case of the Friedreich's ataxia patients. And so with that, I'll stop. Anyone has any further questions? I'm happy to answer them.